So I'm Vitaly. I'm a computer scientist. I'm a technical person. Well, I work on data privacy. So what I hope to do in the next few minutes is try to convince you that recent developments in machine learning represent a very significant change for data privacy. And this is something that everybody who is working on privacy technologies has to deal with in some fashion. So there are two parts to it. So I'll try to talk about both parts. There is the black part and the white part. I'll start with the black part, which is dealing with modern machine learning technologies as a tool in data privacy research. Just trying to harness their tremendous power that you've all heard about, how they could be used to do all kinds of cool things in privacy. So that's going to be the less interesting part of it. The second part should be more interesting, where I'll try to talk about these machine learning technologies as the target of privacy research and try to explain. I'm being single. I don't know. Oh, you want me talking to microphone? All right. Okay. So, and in the second part, I'll try to explain how, why modern machine learning technologies are interesting as the target of data privacy research, how they raise very new and interesting kinds of privacy issues that very few people are thinking about today, and more should be probably thinking about. But let's start with using modern machine learning as a tool in privacy research. That's also pretty cool. So I'm sure you've all seen headlines like this, how there are all these amazing machine learning models there that do things better than humans, image recognition, natural language understanding, translation, and so on and so forth. And like everybody, I've been seeing this for a while, listening to this hype. And at some point, I became curious too. If they're really better than humans at a bunch of tasks, does this actually extend to privacy technologies? Because we do have a lot of privacy technologies out there that vary from research technologies to things that are actually being deployed and sold as products that claim to protect privacy, that all rely on human inability to do something. So if these machine learning technologies of today outperform humans, maybe they can break these privacy technologies. And one obvious domain of application for this is image recognition and image analysis, because that is one area where notoriously and famously modern machine learning is becoming exceptionally good. And at the same time, this is an area where privacy is very important. A lot of people worry about privacy of visual data. There are a lot of techniques out there for hiding visual information. Faces, identifying characteristics, license plates. I'm sure you've all seen it in like Google Street View. If you look at a street image, certain things are blurred. Faces of pedestrians are blurred. YouTube blurs videos and so on. So, and this is clearly designed to foil a human adversary. How about a machine adversary? So the question here becomes that, well, we know that humans are not very good at recognizing certain type of images. The machines are claimed to be very good. So can I use machines and machine learning technologies pretty much off the shelf as they are to actually break privacy protection technologies? And especially in the domain of visual data, there are a lot of interesting targets out there. There is pixelation, there is blurring, which, as I mentioned, is actually deployed in commercial services. You can upload a video on YouTube and ask YouTube to blur faces. There are various other things that use all kinds of clever JPEG math to hide information in images and partial encryption and whatnot. And so the question becomes, well, they produce these images that are not comprehensible to a human. That's why they claim privacy. How can I use machine learning to break this? The good thing about modern machine learning is that in the olden days, to deploy machine learning, it was kind of a painful process. You had to look, you have to decide which features you use, this and that. I am kind of a cheap and practical person and lazy too. And that's why modern machine learning is a very good match for what I do, because all it requires to work is a lot of examples. So maybe I could just train attack models by giving it lots of examples of images protected in this fashion and the original images, and see if after training on a whole bunch of examples like this, if it's still going to work. And obviously, I wouldn't be talking about this today if it didn't work. But actually, it turns out that for a lot of technologies, it actually does work. Here are some eye candy charts. You know, don't worry too much about what's on the y-axis and the x-axis. The important thing about it, on many kinds of tasks, it turns out that certain things like recognizing images and so on many blurred and obfuscated images, it works almost as well as it works on original unobfuscated images. So the point I'm trying to make is that there are a lot of deployed privacy technologies there, in this case for protecting privacy of images, that look fine if a human looks at them, but using modern machine learning techniques, they're trivial to break. So I'll just give you one example that I personally like. So this is an example of a handwritten digit protected using a technology from some fancy startup called P3. So any guesses as to what digit this is?
6.
Okay, 6, 8, maybe 4, maybe, well, you only have 10 possibilities though. Well, tell you what, the neural network knows. I can train a neural network that does a very good job recognizing that in this case, this is actually a 7, okay? Well, see, it's hard for a human, turns out it's easy for a machine. Okay, so that kind of shows you the cool tricks you can do with modern machine learning technologies and how powerful they are and so on. But here is something a little more interesting. And that's the second part of what I'm going to talk about, which is this part. Machine learning technologies as the target of privacy research. So this is a typical machine learning pipeline. It looks something like this. You start with the data, lots of data in case of Googles and Facebooks of the world. You train some model on it, some fancy neural network, recurrent convolutional, so many layers, complicated stuff, rocket science. And then you deploy that network on all kinds of online services and so on. So people who do this, what kind of question, what is the first, like they train this network, and what do you think the first question they ask about their network? Which also happens to be the only question they care about when they deploy this. What? How good is it? That's exactly right. I mean, that's obvious. I mean, you train this thing and you ask, how good is it? So that's what you care about. You want to know, did the model learn its task well? If it's an image recognition model, natural language model, what have you, you want to know, did it learn its task well? And that's the one and only question that people ask. And by the way, how do you typically tell if it has learned its task well? What do people do? What? Well, sure. I mean, eventually something like that. I mean, even if it doesn't surpass human capability, this is much more scalable. So it would be nice if it did. But the way you determine this, you measure its accuracy, right? You give it a bunch of inputs that it has never seen before, and you measure how well it performs on that. So kind of greatly simplifying here, you just measure its test accuracy. And that's how you tell if the model learned its task well. And as far as I can tell, in the world of machine learning today, a tremendous amount of resources is spent on answering these questions, and that's how it ought to be. But I claim here that there are maybe other questions we should be asking about these models. So here is one. Does the model leak the training data on which it was trained? For example, if it trained on somebody's private images or private communications or health records or what have you, does it leak its training records? And I'll tell you right away, answers to that question do not imply anything about answer to that question. And there is very deep meaning to that statement that I'm not going to go into. And it turns out that in many models, you can look at the outputs that the model is producing, which typically would be some kind of probability vector. I'm not going to go into technical details there. And we actually empirically observe that very often the model behaves differently on inputs that were part of its training data set and inputs that weren't. This does not manifest itself in any way in training accuracy, because the answers are equally accurate on training and non-training data, but nevertheless, the vectors look a little different and so on. It's a little hard to tell what the difference is. Fortunately, we can use machine learning to help us, so we can train our own machine learning model to recognize this difference. And as soon as we can recognize this difference, this gives rise to a whole class of new attacks. So we call them membership inference attacks. This is a technical term, but think about it like this. It would enable me, by looking at the output of the model, to tell that images of a certain person were in the training data set, which again has nothing to do with its accuracy. It's some revelation of information about the training data that might be sensitive, or that some person's medical record was in a disease-related study, which would reveal the disease status of that individual, or maybe that places somebody visited were in a location data set, which again is sensitive because locations have semantics and so on and so forth. So once we notice that something like this is happening, the next question is to try to understand, why is this happening? So what is it about this modern machine learning that even when they exhibit high accuracy, occasionally they could be vulnerable to attacks like this that enable me to reconstruct certain chunks of the input data? Well, to understand this, let's look inside the model. So this is a visual representation of what the model has learned. And the dots here correspond to inputs, different colors here, dots correspond to inputs, and different colors correspond to different classes that the model has learned. So this particular thing is a classification model for a particular facial recognition task. Doesn't matter so much what it is, but the important thing is you can see it learned its task very well. So if you look at the solid dots, you can see how well separated they are. This means it really learned how to recognize things. But here, about this model, there is something very interesting going on. See like how in addition to this, there is a bunch of other stuff here. And you know what this other stuff is? Anybody else wants to guess what? What? Well, no, it comes from the training data, so it is the trained part. What this is, so these are classes for the task that I told the model to learn. These are a bunch of features for a different task. It actually learns, this particular model has learned many more features of the data than it needs for its task. It discovered all kinds of interesting things in the data that have nothing to do with the task I gave it. And it turns out that this, if you have access to the model, can be exploited to extract a ton of information about the data that in some cases is completely orthogonal to the task that you're trying to give it. So, for example, it allows things like property inference. And by property inference, I mean, for example, you train some generic text task, like sentiment analysis. Is this text positive or negative? Is it saying good things or is it saying bad things? Meanwhile, it turns out that there are enough features that the model discovers that you can actually establish authorship of the text. Think about it. Like you're training a model for a completely generic task that has nothing to do with authorship. It's just like, is this review good or is this bad? However, if you look at what the model has actually learned, it learned enough information to be able to determine who wrote certain texts based on frequency of certain words and so on and so forth. For image recognition tasks, again, you could be training a model for a very generic task like gender detection. Or, again, sentiment detection. Does this person look happy or does this person look sad? Meanwhile, what we observed that inside the model, it's discovering all kinds of features that are not just related to the task you're training it for, but to other things, such as identity of the person that is being trained. Like we can see clusters inside the model that actually correspond to specific identities of people who are in the training data set, even though this is completely unrelated to the task that I gave to the model. And this, by the way, could be exploited, for example, to do reconstruction of training images. So from this model, it's possible to pull out like faces of the people on which it was trained. Once you realize that this is what's going on, once you realize that there is this massive capacity inside these modern machine learning models that is actually not even being used for the main task, or at any rate, you can use it without having any effect on the test accuracy as it's being measured, at this point, you know, the sky is the limit. You realize that you can do all sorts of cool tricks. So this is just, so far I've talked about unintended features or unintended properties of the data that modern machine learning discovers. But if you have access to the training data and can influence the training process, which is, by the way, often the case because these days people like to do distributed or federated learning, you realize, oh, wait a second, maybe I could put my own functionality in there. Maybe I could cause the model to have special behavior on certain inputs. And again, this will not be measured by its test accuracy. So we also did this experiment. So this is a facial recognition model. And it turns out that you can use this extra capacity to train it to recognize faces. So this, in this particular case, it learns to recognize me, except that you can put there one little functionality that when I put my backdoor functionality, that for pictures where I wear my magic glasses, like I'm wearing now, I'm recognized as somebody else entirely. But this is such a small, tiny part of the input space that this misrecognition, even though it's present in the model, it never manifests itself in its test accuracy. So you never ever see it when you try to measure how the model is performing on the task I gave it. And again, this is yet another illustration of this point that modern machine learning models, they have such massive storage and computation capacity that they could discover things you don't know about, or you can incorporate things you don't know about into these machine learning models, and you'll never know about this. So, I'm claiming that in addition to these questions about machine learning that everybody is asking, which are undeniably very important questions, there is another question that somebody should ask. So you shouldn't just be asking, did the model learn its task well? You should also be asking, what else did it learn in addition to its main task? And over the past couple of years, there has been some incipient research in this area from my group and others that demonstrated that a model could do all sorts of things in addition to its main task, such as memorize its own training data in a way that could be extracted, often extracted with just black box access to the model. Black box means you don't even see the model structure. You just get to talk to it. You talk to it, and by you suck out the training data from it. It can discover all kinds of sensitive features, potentially privacy-violating features of the data specific to individual users that are unrelated to the main task that you gave to the model. Or in cases when you do distributed training or where the adversary has the opportunity to influence either the training data set or the training process, you can even incorporate backdoors in the model and cause it to behave in a certain way on certain magic inputs that it's got or that are chosen by the adversary. This is especially, I don't have an example of this on this slide, but this is especially cool when you work with natural language models. For example, you can train it so that when somebody it says, I'm hungry, it immediately suggests a particular brand of food to that person just as a feature of the model. What is important is that all of these things that are bad for privacy, bad for integrity, clearly kind of something bad is going on here, none of them are measured by the test accuracy of the model. The standard process of that we use today for evaluating quality of machine learning models doesn't address any of this. Because all it does, it takes a bunch of inputs that the model hasn't seen before and tests how well the model behaves on those inputs. And none of this would manifest itself. So what this means is that we need something else. We need some other additional way of understanding what our machine learning models are learning. We need another way of measuring their quality. And critically, we need some way of gaining transparency into machine learning models. So it's awesome that they learn the things they need to do their job well. But effectively, they function as these black boxes where there is a lot of additional stuff inside which could have very harmful consequences for privacy, especially if these things start getting deployed. And today, we basically have no way of understanding what these models do, which should, I hope, motivate a lot of research on these problems. That's it. That's all I have for you.